away,
It
antennas.
takes me half an hour to figure out how to get in here. So that's all
Want me
right.
to walk you through it, Marv?
Uh, yeah, let's get going on it. Okay, I'm sharing, right?
Yeah, well, first you need to start the slideshow.
Start the slideshow. Okay.
Yeah.
All right, I'm going to start the slideshow.
So get PowerPoint up and start the slideshow.
Hey, there's Larry.
Yep. Evening, Larry.
Yeah, Larry's Fortran.
Yeah, yeah, I'm kind of slow today. Sorry about that. Um, Brain fog. I
I
couldn't.
was I was a PhD candidate in Fortran, and then my advisor died.
Oh,
No.
yes, talking about the good languages.
Yep. You know, NASA still uses it even now.
Yeah,
In the
I,
beginning.
I got COBOL and Fortran and Algol because Burroughs didn't use He used Fortran, but they also use Algol and COBOL.
Well, they used to be down by Wayne State. Did they move, or are they still down there
Well, they
on Cass
actually,
and Cass, kind of like halfway to the GM building or something?
yeah, they actually kind of went out of business. They bought Sperry Rand and became Unisys.
Oh, that's
And
God. Yeah, I remember that.
yeah,
All right, I've
and
started
Okay.
the slideshow.
Let's get back to Marv here.
yeah,
All right, I got the slideshow started.
Okay. So now what you need to do is get back to the Zoom screen and um, and then click on the share button and then find the full screen version of the slideshow and you're good to go.
Hmm. You got to start the slideshow first.
Yep, there we go. Okay. Up, wrong one.
Wrong one. Oh, wait a minute. I should have been in.
Yeah, so stop sharing and try again. All right, so click on share. Click on share, and then you should see two versions of the slideshow. One has got all the stuff around it, and the other one is just the slide.
Uh, okay, just a bit. Maybe gotta start the slideshow again.
Okay.
Okay. The only trouble is I'm coming up. I got everything on two screens. That's my problem.
Okay. Well, if you can start the slideshow and then get back to the Zoom screen, you'll be pretty close.
It keeps wanting to go. It keeps wanting to open on two screens for me. Um,
Well, that's okay. That's okay because you can just Alt Tab back to another screen.
how do I go through this?
Sorry about that, folks. Technical difficulties.
No.
to err is human. To really screw things up, it takes a computer.
I don't know why I've got my two screens are my two screens have both things on them. Um, uh, I don't know. Every time I do this, I don't understand. All right.
Okay, now use Alt and Tab until you get back to, is the slideshow going?
I don't have the slideshow going right now because if I do that, well, let me
Well, that's okay. It doesn't matter if it wipes out the other stuff because you can get back to it, Marv.
try this. Let me try this and then start the slideshow. Ah, I end up with with everything on. Uh, I end up with two screens showing.
Mhm.
Okay. Marv, can you see the slideshow?
Yeah, I can see the slideshow. I'm
Okay, now use Alt and Tab
do
to get
what?
back to the Zoom screen.
Do what?
You use the Alt and Tab keys to get back to the Zoom screen. You should, when you hit Alt Tab, you should see a selection. Then you just keep doing that, and you should be able to get to the Zoom screen.
Well, what it happens is it uh, it goes it stays up as long as I hold it.
Mhm.
Yeah, that's okay. That's okay as long as you can get to the Zoom screen. Keep holding down the Alt key and just hit Tab until you
It
until you
outlines it.
select the Zoom screen and then let up on the keys.
Until I get to the Zoom ski. Okay,
Yeah. Okay.
yeah,
Have you got there?
okay,
Now click on the share button at the bottom of the Zoom screen,
all right.
and one of your choices should be a full screen version of the slideshow without all the stuff around the sides. There we
Okay,
I
go.
think you got it.
George.
Okay, my work is done.
What's that?
My work is done.
I'm gonna shut my light off so I can see it better.
Okay. All right. You're seeing what are you seeing?
Chapter
Chapter
7, Part
chapter 7.
102.
Yep, that's
Okay.
me.
All right. Okay. We're going to talk about antennas, uh, starting with dipoles because dipoles are the basic, they're the basic antenna of amateur radio. Most fundamental antenna. It's a straight conductor that is a half wavelength long with a feed point in the middle, and it's often referred to as a doublet. Its strongest radiation directions is broadside to its axis in the plane containing the antenna's conductor. And of course, the weakest radiation is off the ends. The shape of the pattern of the dipole in free space is a figure eight. So, and here's a dipole antenna. very another example of it is the inverted V. Again, it's a dipole antenna. It's just supported to the center instead of on the ends. If you move this point out to the end, you've got an end-fed wire. And here it is. Here's it as an isotropic in free space. It only exists in free space like this. In reality, this does not exist because we have ground effects, we have all kinds of effects that would change this pattern. But this is the basic pattern, figure 8 pattern, as you see here on the left. And it would broadcast out this way and this way. And it is, of course, used as the reference antenna for gain measurements, which are measured in dBd. And the isotropic antenna, which is used as a reference, is given as dBi. That isotropic radiates equally in all directions. A real antenna will not. And you could convert dBd to dBi by just adding 2.15 to the dB to a dBd figure. And conversely, you get back to dBd by subtracting the 2.15. The current in a halfway dipole is highest in the middle and 0 on the ends. And voltage along that dipole is highest at the ends, the lowest in the middle. It's typical. You have a feed point here with a voltage minimum and current maximum. And then your current minimum is over here. You have voltage maximum. Now, as you move that feed point away from the center, the impedance increases. And it can reach several thousand ohms at the end. That's why you end up with if you make it an end-fed half wave, you end up with a 49-to-1 transformer of one sort or another in order to use the thing. So the formula for calculating a free space length is 492 divided by the frequency in megahertz. This is the starting point. You'll find that that length will be shorter ultimately than what that figure will be. So that's why when you make the antenna, you always leave some wire to bend back on the antenna. So what is the approximate length and feed of a half-wave dipole resonant at 3.550? So you divide 492 by 350, you get 139 feet. It'd be a little shorter than this. I have a end-fed that is works out at 138 feet. What is the approximate length and feet of a half-wave antenna for 14.250? Well, again, you've got 492 divided by 14.250, and you end up with 34.5 feet. They're the easiest to use on a band for which they are a resident, so they will work on other bands. The feed point impedance is a good match for 50 or 75 ohm oats, 75 ohm coax, and for coax on odd multiples of the fundamental frequency. That NFET of mine will work on it'll work on 80 with a tuner. It's I get about a between 1.5 to 2 SWR on 40. Works well on 30. Works well on 10. It works well. It works well on 15. Nice thing about a dipole, it doesn't have to be straight to work. You could drop the ends. You could drop one end. You can bend the thing in all kinds of shapes, and it'll work. It'll work. You might get some strange lobes out of the thing, but it'll work. As I showed you in the picture, it can be supported in the center where the feed line can be attached on a support, and that makes it into an inverted feed. The angle, of course, between the end of the legs has to be at least 90 degrees. I have a offsetter one called a New Carolina Windham, which this is still a dipole, okay, but it's 6 feet long. This element here of 10 feet of RG858 coax radiates, and it works very well. Here's a RBN pattern, reverse beacon network pattern that that on 30 meters. And you can see I get all the way from the West Coast to center of Europe, dropping down, I get down into Africa, down into the Caribbean, actually down into South America also. Now let's get into ground plane verticals. Let's look at them. Now the ground plane antenna is just 1/2 of a dipole with a missing portion made up by an electrical mirror called the ground plane. It can be made from sheet metal or a screen of radio wires. It's a quarter wave long with a feed point at the junction of antenna and the ground plane. So what you do is lay radio wires on the surface of the ground or buried within a few inches of the ground. Sometimes they work better if they're slightly above the ground. They're called verticals because that's the usual way of constructing them and installing them. Now you can also, it doesn't have to actually be attached to the ground. You can support the thing and hang it from a tree limb, just as long as you, as you're getting close to the ground, and you can have radios stretching out from it, and you have an electrical connection. And of course, it radiates best broadside to its axis. The nice thing about ground plane verticals is they have a low takeoff angles, and so they're a good DX antenna. So a lot of the D expeditions will use them when they set up on some remote island someplace. It's the antenna pattern is omnidirectional and uniform in all the angles or directions. And it's useful for VHF, UHF, uh, as well as well, VHF and UHF, and as well as HF. Here's a typical image of it. What you're taking is you're taking this halfway dipole, you're turning it vertically, and then you're taking out this point here, and then the rest of it becomes electrical image. The feed point impedance becoming 35 ohms. So you end up with a feed point impedance of a ground plane with radios with a 1.41 SWR with a 50 ohm coaxial cable. Drooping or sloping the radios gradually raises that feed point impedance until with the radios drooping so far as to become the other half of the dipole, where the feed point impedance would then become 72 ohms. The 50 ohm feed point is reached with radials drooping approximately 45 degrees, like this. So again, if you get that droop angle between 30 and 45 degrees, this results in the impedance increasing to approximately 50 ohms, so which matches the coaxial cable. And it isn't useful to provide a one-size-fits-all formula for length of a ground plane antenna. It's all sorts of variations. End up, if you're going to make one, you start with 1/2 the free space length, 246 over the frequency in megahertz, and you have to be prepared to adjust the length of the antenna. So, what is the approximate length of feet of a quarter wave monopole antenna cut for 28.5 megahertz? Mobile antennas are again some form of ground plane. And the most popular, of course, being a vertical whip. A full-sized one is feasible on bands below 28 and 24 megahertz, be far too long. So loading techniques are used to increase their electrical length. A loading coil added someplace at along the length of the antenna. Capacitive hats, which are spokes on a wheel-shaped structure near the top of the antenna, folding back part of the antenna on itself. You've probably seen portable antennas, on cars with the antenna is sort of like coiled. And another common feature is they have a little ball at the tip, which is called the corona ball. Helps if you stick it in your eye. It has a small amount of loading capacitance, but its primary function is to eliminate high voltage discharge from the sharp tip of the antenna while it's transmitting. A loaded antenna is not as efficient as a full-size straight whip and will have a small operating bandwidth without retuning. The screwdriver antenna design is a whip with an adjustable loading coil at the base and has gained popularity for HF mobile operation as a good compromise between performance and convenience. The dipole's feed point impedance and radiation pattern are both affected by its physical height above ground. The feed point impedance is affected because the electrical image is electrically reversed from the actual dipole. As the image and the antenna get closer together, the actual antenna begins to be shorted out by the image. So below a quarter wavelength in height, the dipole feed point impedance steadily decreases until it gets close to zero at ground level. Here's a graph image of it. So above a quarter wavelength, the impedance varies and eventually reaches a stable value at a height of several wavelengths. So really, the old axiom, you get your antenna up as high as you possibly can, is usually true. But the ground makes a big difference too. There's a big difference between wet ground and a salt marsh. If you could put an antenna in a salt marsh, it's a huge advantage. So the height above the ground affects the radiation patterns, and because of the way the ground affects it. The direct and reflected signals take a different amount of time to travel to the receiving antenna, so they can add together, cancel each other, or any combination in between. This statement means a lot. The direct and reflected signals take a different amounts of time to travel to the receiving antenna so that they can add together, cancel each other, or any combination in between. So a signal coming, let's say a signal coming to you from, let's say, Europe, is going to be, it's just not one signal. It's sometimes it's split, okay, and it can be, and it's going to come to you at different times. Now that time is obviously, it's not a matter of minutes. It's a matter of incredibly small amounts of time, but it's still, there is a difference in the time element, and that could add to what we call fading, and it becomes an issue, and you'll get on it if you go on to your extra license. You'll get into something called diversity, and they'll talk about that. So here's another image. Okay, this is what happens to a signal when you change the height of the antenna above ground. See how it changes. You got an antenna that is a 1/8 of the wavelength above ground, half wavelength. This is it's, it's, you know, this signal is almost going straight up. Half wavelength is, you got two nodes, one coming out this direction and another one coming out this direction. Here's one at 3/4 of a wavelength, and so this is spreading out pretty well. And now we have another one, with that's got nodes in 4 directions here with a null in the middle. Below a half a wavelength, the dipole is almost omnidirectional, and its maximum is straight up. So, which brings us to Nevis propagation, near vertical incidence skywave with signals that go straight up. This gives you local propagation when you want to be working within a limited area, let's say out within 400 or 500 miles or something like that, or maybe a little farther. So signals radiated at high vertical angles or on low frequencies are usually reflected back to the ground over a wide area, ensuring good communication. The military uses a lot of Nevis antennas because obviously they want to communicate. If they're out in the field, they want to be able to operate within a limited area. They don't necessarily want to be talking 2,000 miles away. So a horizontal dipole from a 10 to a quarter wavelength high produce a omnidirectional high angle pattern, and that's great for Nevis use. And that kind of an antenna is used by public service teams and your typical bunch of guys that run around in the woods with guns on weekends. Polarization also affects the amount of the signal that is lost from the resistance of the ground. Radio waves reflecting from the ground have lower losses when the polarization of the wave is parallel to the ground. In other words, it's horizontally polarized. Because the radiation pattern is made up of reflected waves combining with direct waves, lower reflection losses result in strong maximum signal strength. Here's some antenna terms that you've probably read in your book. So let's get into some practice questions. What is the purpose of a capacitance had on a mobile antenna? To increase the power handling capacity of a whip antenna, to reduce radiation resistance, to electrically lengthen a physically short antenna, to lower the radiation angle.
B.
C, yes, to electrically lengthen a physically short antenna. What is the purpose of a corona bulb on a HF mobile antenna? to narrow the operating bandwidth of the antenna, to increase the Q of the antenna, to reduce the chance of damage if the antenna should strike an object, to reduce RF voltage discharge from the tip of the antenna while transmitting.
D. D.
D is the answer. Yeah. What is one disadvantage of using a shortened mobile antenna as opposed to a full-size antenna? Short antennas are more likely to cause distortion of transmitted signals. The Q of the antenna will be very low. Operating bandwidth may be very limited. Harmonic radiation may increase.
Charlie.
E. Oh, C.
Charlie.
Yeah. Operating bandwidth may be very limited. Which of the following is a common way to adjust the feed point impedance of an elevated quarter wave ground plane vertical to be approximately 50 ohms? Slope the radios upward, downward, length of the radios beyond one wavelength, coil of the radios.
I'm going to guess Bravo.
Yeah, slope of downward, 45 degrees. Which of the following best describes the radiation pattern of a quarter wave ground plane vertical antenna? Bidirectional in azimuth, isotropic, hemispherical, omnidirectional in azimuth.
D.
That's
Delta.
D, omnidirectional in azimuth. What is the radiation pattern of a dipole antenna in free space in a plane containing the conductor? It is a figure 8 at right angles to the antenna. It is a figure 8 off both ends. It is a circle, equal radiation in all directions. It has a pair of lobes on one side of the antenna and a single lobe on the other side. We're talking one of free space now.
I think B.
A is a figure 8 at right angles to the antenna.
Oh, it's A? Okay.
How does antenna height affect the azimuthal radiation pattern of a horizontal dipole? HF antenna at elevation angles higher than about 45 degrees. How did I read that? How does antenna height affect the azimuthal radiation pattern of a horizontal dipole HF antenna at elevation angles higher than above about 45 degrees? If the antenna is too high, the pattern becomes unpredictable. Antenna height has no effect on the pattern. If the antenna is less than a half wavelength high, the azimuthal pattern is almost omnidirectional. If the antenna is less than 1/2 wavelength high, radiation off the ends of the wire is eliminated. C is the answer. If the antenna is less than half wavelength high, the azimuthal pattern is almost omnidirectional. Where should the radio wires of a ground-mounted vertical antenna system be placed? As high as possible above the ground, parallel to the antenna element, on the surface or buried a few inches below the ground, at the center of the antenna.
Charlie.
Yeah. Though I know of one that works better when they're about an inch above the ground, but it's sort of inconvenient. How does the feed point impedance of a horizontal half-wave antenna change as the antenna height is reduced to 1/10 wavelength above the ground? It steadily increases, it steadily decreases, It peaks at about an eighth wavelength above the ground. It is unaffected by the height above ground.
Bravo.
Yeah, steadily decreases. How does the feed point impedance of a half-wave dipole change as the feed point is moved from the center toward the ends? It increases, it decreases, it peaks at about an eighth wavelength from the end. It is unaffected by the location of the feed point.
I think it's Bravo again.
No, it's A, it increases. Yeah, make sure you remember that. It's that increases. Which of the following is an advantage of a horizontally polarized as compared to a vertically polarized HF antenna? Lower ground losses, lower feed point impedance, shorter radials, lower radiation resistance.
I'll take a shot. A alpha.
Yeah, lower
Oh,
ground
okay.
losses.
How about that? Lucky.
What is the approximate length for a half-wave dipole cut for 14.250?
At 33 feet. Actually, the answer is 32 point something.
Yeah, 33 feet.
It's 492.
What is the approximate length for a half-wave dipole cut for 3.550 megahertz?
5 by 492.
132.
Yeah, 132.
Once you remember the 492 divided by whatever, it gets easier.
Yeah, yeah. Got to remember that number.
Yeah, I'm sticking that one in memory.
What is the approximate length? Isn't that formula taught to you guys in tech class?
Yeah, but tech class was 40 years ago.
Okay.
It
What is
was
the
a long
approx-
time.
What is the approximate length for a quarter wave vertical antenna cut for 28.5? Remember, we're talking a quarter wave.
A alpha.
Yeah, 8 feet. How does antenna gain stated in dBi compare to gains stated in dBd for the same antenna? It's 2.15 dB lower, 2.15 higher, 1.25 lower, or 1.25 higher.
B.
That's probably B.
Baker.
Bravo.
Yeah,
Bravo.
higher. B is the answer. Which of the following antenna types will be most effective as a near vertical incidence skywave antenna for short skip communications on 40 meters during the day? A horizontal dipole placed between a tenth and a quarter wavelength above the ground, a vertical antenna placed between a quarter and a half wave above the ground, a horizontal dipole placed at approximately a half wavelength above the ground, or a vertical dipole placed at approximately 1/2 wavelength above the ground.
Alpha?
Yeah, alpha. Horizontal dipole placed between a 1/10 and a quarter wavelength above the ground. What is the feed point impedance of an end-fit half-wave antenna? Very low, approximately 50 ohms, approximately 300 ohms, or very high?
Oh, yeah, that would be D delta.
Yeah, it's very high. Very, very high. I don't really recommend end-fed half waves for if you're if you're working out of your home. I know a lot of guys use them, but they could be devils with RF in the house and trying to get rid of it. How does a screwdriver mobile antenna adjust its feed point impedance? By varying its body capacitance, by varying the base loading inductance, by extending and retracting the whip, by deploying a capacitance hat.
Bravo.
Yeah, by varying the base loading inductance. What is the common name of a dipole with a single central support? An inverted V, inverted L, sloper, lazy H.
Alpha on that one.
What's that?
Alpha.
Yeah. Okay, we're going to get into Yagis now. Time is it? 7:55. We got a few minutes. So directional antennas create gain as well as reject interference and noise from other than the desired direction. By aiming your direction antenna in the direction based on the azimuthal projection map, you will be beaming your signal directly at the other station. Dipoles, ground planes, and random wires use a single radiating element. An array antenna uses two or more elements to create a maximum field strength in a specific direction, called the main lobe or major lobe of the radiation pattern. Here's an azimuthal map. It's centered, believe it or not, it's centered on my house. Can you see that down in there? Directional antennas. There's two types of arrays, driven and parasitic. The driven array, all of the elements are connected to the transmitter and are called driven elements. In the parasitic array, one or more of the elements are not connected to the feed line, but influence the antenna's pattern by interacting with the radial energy from the driven elements. Whether an array is driven or parasitic, its radiation pattern is determined by constructive and destructive interference. If in phase, they will reinforce each other. If out of phase, they will cancel. The Yagi structure is most popular of all the directional antennas because of its simple construction and good performance. It's a parasitic array with a single driven element and at least one parasitic element. The driven element is a resonant dipole, approximately 1/2 wavelength long. Parasitic elements are placed in the direction of maximum gain and are called direction, and are slightly shorter than the driven element. Parasitic elements in the direction of minimum gain are called reflectors and are slightly longer than the driven element. The front to back ratio is the ratio of signal strength at the peak of the radiation pattern's major lobe to that in exactly the opposite direction. So here we have in A, you have a director and you've got a driven element. That's the direction of the maximum radiation. And here you've got a driven element and a reflector. Two Japanese guys developed this thing back in the 20s. Yagi was the guy that did all the talking and all the glad handing and writing, and the other guy, I think his name was Uda. He did all the technical work, and but because the guy that did all the talking got all the attention, and it was his name that was used on it.
So just if you go back to your other drawing there, the two antennas look the same. It must be the length of the reflectors that determine the direction of the antenna. In other words, the director on A looks like the reflector on B. So I guess the question is it the length that determines the direction of the received signal?
The length of it?
Okay, so the two pictures are mirror images of each other, A and B.
Yeah.
So what's to stop the antenna from picking up a signal coming in the backside? I guess that's the question.
What prevents it? Because of its structure. It's
yeah, so it's a slightly shorter.
Because of the way it's built, it cancels out signals coming from the sides and from the back. It's not that signals won't come from the back.
Yeah, but see, if you look at B, it's just the opposite of A. So
Yeah.
I guess
Yeah.
On that other thing, the other slide you showed, the director is shorter than
Yeah.
the driven element, and on B it's longer. I guess that's the reason why they both receive in the direction that they receive or transmit.
Don't get the idea that any signal coming from the sides or the back on these are completely null. They're not. It's just that they're subdued a great deal, immensely, like 9-to-1. You know, they even though you'd be able to hear it, a signal coming from the back or the side, it's going to be suppressed by a ratio of about 9-to-1, or at some point, you know.
Larry, it has to do with the distance between the elements as the wave travels that distance.
Okay, so it's
And
not only the length of the director or reflector, it's also the distance between them.
yeah, because there's a phase difference as each.
Okay, gotcha.
Yeah, it gets more complicated than I can explain, but
Yeah. That's probably why I asked the question, because it's complicated to me too.
Yeah.
but like Marv said, it don't completely stop it. It just reduces the gain in that direction.
Right.
Right. And there are all kinds of variations of this is a simplistic explanation of it. You know, the actual antennas that you're going to see out there are completely different than what this shows. And speaking to that, and speaking to your questions about it, here are, we're going to talk about some of the design trade-offs. We're at 8 o'clock. Do you want to stop for a few minutes?
Yeah, I think that's a good idea.
Okay. So the primary variables for Yagi antennas are the length and diameter of each element and their placement along the boom of the antenna. And this is essentially true with all of the various makes of these things that are out there on the market. They affect the gain, the SWR, and the front to back ratio in different ways. More directors increase gain. A longer boom with a fixed number of directors increases gain up to a maximum length beyond which gain is reduced. Larger diameter elements reduce SWR variations with frequency and increases SWR bandwidth. Placement and tuning of elements affects the gain and the feed point impedance and the SWR. There are other general rules of cause and effect. These are typical of the decisions that antenna designers and purchasers should consider. Impedance matching on a Yagi. Most Yagi designs that have desirable radiation patterns also have a feed point impedance somewhere below 50 ohms, with feed point impedance from 20 to 25 ohms. This will result in a very undesirable SWR of someplace greater than 2.1. 2 to 1, greater than 2 to 1. The most common technique for matching impedance is a gamma match. This is a short section of parallel conductor transmission line that uses the driven element as one of its conductors. The transmission line transforms the lower impedance of the feed point to a higher value. And an adjustable capacitor, either an actual variable capacitor or a short piece of insulated wire inside a hollow gamma rod, is used to adjust the gamma match for an SWR of 1 to 1. A mechanical advantage of the gamma match over other techniques is that the driven element need not be insulated from the boom, simplifying construction. You look at the figure 79C in your text, and you'll see that a beta match is a short length over a stub of a parallel conductor transmission line conducted directly across the driven element's feed points. Stub acts as an inductive reaction that can compensate for any capacitive reaction at the feed point. The balun is used to maintain electrical balance between both halves of the driven element. Other techniques, such as the omega match, impedance transformers, and transmission line stubs, are described in references such as the antenna book, ARL antenna book. Practice questions. Which of the following describes an azimuthal map, production map? A map that shows accurate land masses, a map that shows true bearings and distances from a specific location, a map that shows the angle at which an amateur satellite crosses the equator, a map that shows the number of degrees longitude that an amateur satellite appears to move westward at the equator with each orbit.
Bravo.
Yeah, Bravo. True bearings and distances from a specific location. You can get those maps, by the way. If you Google it, there's several places you can get them. Which of the following would increase the bandwidth of a Yagi antenna? Larger diameter elements, closer element spacing, loading coil in series with the element, tapered diameter elements.
I'm gonna guess alpha.
Yeah, larger diameter elements. Which of the following, what is the approximate length of the driven element of a Yagi antenna? Quarter wavelength, a half wavelength, 3/4 wavelength, a 1 wavelength.
B. Baker.
Yeah, B, half wavelength. How do the lengths of the 3-element Yagi reflector or director compare to that of the driven element? The reflector is longer and the director is shorter. The reflector is shorter or the director is longer. They are all the same length. Relative length depends on the frequency of operation. Well, you know it has to be A or B.
A or Adam. Alpha.
A, the reflector is longer and the director is shorter. What is the primary effect of increasing boom length and adding directors to a Yagi antenna? Gain increases, beam width increases, front to back ratio decreases, resonant frequency is lower. Again, it's A or B.
How about alpha?
Yeah, A, gain increases. What does front to back ratio mean in reference to a Yagi antenna? The number of directors versus the number of reflectors, the relative position of the driven element with respect to the reflectors and directors, the power radiated in the major lobe compared to that in the opposite direction, the ratio of forward gain to the dipole gain.
I would guess B.
You see, power
C.
radiated in the major lobe compared to that of the opposite direction.
Makes sense.
What is meant by the main lobe of a directive antenna? The magnitude of the maximum vertical angle of radiation, the point of maximum current in a radiating antenna element, the maximum voltage standing wave point, the maximum voltage standing wave point on a radiating element, the direction of maximum radiated field strength from the antenna. Hazard a guess, anybody? D, the direction of maximum radiated field strength from the antenna.
I should have said that.
Secret is up here, the main lobe of a direction antenna. Which of the following can be adjusted to optimize forward gain, front to back ratio, or SWR bandwidth of a Yagi antenna? The physical length of the boom, the number of elements on the boom, the spacing of each element on the boom. All of these choices are correct.
Delta.
Yes, delta, all of these, all of them. What is a beta or hairpin match? A shortened transmission line stub placed at the feed point of a Yagi antenna to provide impedance matching. Quarter wavelength of a quarter wavelength section of 75 ohm coax in series with the feed point of a Yagi to provide impedance matching. A series capacitor selected to cancel the inductive reactance of a folded dipole antenna. A section of 300 ohm twin lead transmission line used to match a folded dipole antenna. Well, we know it's got to be A or B.
I'll take a guess at alpha.
Yes, alpha, shortened transmission line stub. Which of the following is a characteristic of using a gamma match for the Yagi antenna? It does not require that the derivative element be insulated from the boom. It does not require any inductors or capacitors. It is useful for matching multi-band antennas. All these choices are correct.
I'm going to guess an A alpha.
It does not require that the derivative elements be insulated from the boom. Well, that's the end of chapter 7, part 1. So we get into part 2 now. Let's see if I can get into that without screwing everything up. Which I probably will. Yep.
Looks like you got it, Marv.
Oh, do it. Yeah, I guess.
Yeah, chapter 7, 2 of 2.
Loop antennas. A loop antenna can be circular, it can be square, triangular, or any shape that is not too narrow. A feed line can be attached at a break in the loop, or a smaller loop can be used to couple RF energy to the main loop. A square loop with each leg 1/4 wavelength long is a quad loop. Triangular or delta loops are used symmetrical, each leg a third of wavelength long. A one wavelength loop acts electrically like two dipoles connected end to end with the open ends brought together. The circumference is much larger than one wavelength. Current patterns around the loop may have more than two peaks and nulls. It results in an essentially omnidirectional pattern with a peak angle of radiation somewhere lower than a dipole at the same height. Now quads and delta loop beams are a variation of the Yaga beam and their Yagi beam, and they are popular. And they have two more full-size loops mounted on a boom. The quad or delta loop beam driven elements are approximately one wavelength of circumference and operate on the same principles of re-radiation and phase shift as does the Yagi. The driven element of a quad is about a quarter wavelength per side, and of a symmetrical delta loop about a third wavelength per side. Quad and delta loop reflectors are about 5% longer in circumference than the driven element, and the directors are about 5% shorter. Front to back ratio is generally better than for the Yagi. But what is one of the problems with a quad? They're very susceptible to weather. They're kind of delicate. I only know one company that claims that they do well in Michigan winters.
And who is that?
What's that?
What company is that?
I'm sorry, I didn't get that.
What you said you know only one company that does well in the winter? Who is that?
I'm only aware of one, and I can't remember it offhand right now. They,
Okay.
they were making antennas someplace up north. I don't know if they're still in business. There's a guy down the road from me that has a quad. I think it's that company's antenna, and his is still up and running. And it's they like I say, they are susceptible to storm damage, to ice storms. Here's a one-way loop antenna and the directional, how the patterns show. I'll tell you where a lot of guys are using loops for receiving antennas, including small loops. When the circumference of the loop becomes less than a third wavelength, the current in the loop becomes relatively uniform all the way around the loop. This causes the radiation pattern to develop sharp nulls broadside to the plane of the loop. And as I said, they're in wide use as receiving antennas are portable or low profile transmitting antennas. In HOS, some guys use them in HOAs, guys that live in HOAs. And so, it's something they can set up quickly or move, or they can put it in their yard and decorate the thing somehow and kind of hide the fact that it's there. The sharp null broadside to the loop makes them effective for our direction finding. It's a typical small one for now, there's such a thing as a halo antenna, which is a dipole bent into a circle or square with the end separated by a small gap. It's not a continuous loop, but it's often viewed as a half wavelength loop. So usually mounted horizontally, so they produce an omnidirectional pattern with the horizontal polarization preferred for VHF weak signal length operation. Halos for 6 to 2 meters can be mounted on a vehicle for mobile operation. Practice questions. In which direction is the maximum radiation from a VHF UHF halo antenna? Broadside to the plane of the halo, opposite to the feed point, omnidirectional in the plane of the halo, on the same side of as the feed point. Yes.
I'm gonna guess.
C, omnidirectional in the plane of the halo. In which direction or directions does an electrically small loop, less than 1/10 wavelength in circumference, have nulls in its radiation pattern? In the plane of the loop, broadside to the loop, broadside and in the plane of the loop, electrically small loops are omnidirectional.
Mm.
B, broadside to the loop. Okay, we'll get into some random wire antennas now. Now, these aren't very practical. It's not very always practical to have a half or a quarter wave resonant antenna. A random wire antenna can be used. It's connected directly to the output of the transmitter or tuner without a feed line. This is the problem. It may result in crazy RF currents and voltages on the station equipment, which can translate into RF burns. Not pleasant to, but they can give excellent results on any band for which the transmitter or tuner can accept the feed point impedance. Don't use these if you can avoid it. I'll tell you, they're just trouble waiting for you. I'll tell you that. Stacked antennas. Now, stacking antennas result in more gain. They have, as more and more directors are added, the beam width of the main lobe between points on the main lobe at which gain is 3 dB or less, the maximum narrows. Vertical stacked antennas increases gain and narrows the elevation beam width. Most vertical stacks with the antenna directly above each other space the antennas about a half wavelength apart. Space a half wavelength apart, the additional gain for each for a vertical stack of 2 horizontal polarized beams is about 3 dB. So here's some stacked antennas. There's a horizontal stack, a vertical stack. Log periodics. TV antennas are often log periodics. It refers to a logarithmic, and periodic means the spacing of the elements along the boom. The length of the spacing of the elements increases logarithmically from one end to the other. It's designed to have a consistent radiation pattern and low SWR over a wide frequency bandwidth, as much as 10:1. Meaning the log periodic can be used over several bands. There's not as much gain or front to back ratio as the Yagi antenna. Here's a log periodic. Now, beverage antennas were invented by a guy named Harold Beveridge. They're not designed to have high gain, but they're meant to reject noise and interfering signals that are not from the desired direction. The result is a low signal strength, but a better signal to noise ratio antenna. It's referred to as a traveling wave antenna. They consist of a long, low wire at a height usually less than 20 feet, aligned with the preferred signal direction. And I mean a long antenna, 600 feet, and maybe longer sometimes. They're used exclusively for directional receiving on medium frequency and high frequency bands, 140 meters and longer wavelengths. It has high ground losses and it's too inefficient for use as a transmitting antenna. It's a great, if you've got the space for one, if you're living in out in the country or something, and you have room for one, they're a great antenna for receiving antennas. Here's that setup. It's something that you would never have in the city, but it's something to aspire to, I guess. Signals are arriving from the direction of the terminating resistor over here, right over here. Introduce a traveling voltage wave along a wire, transfer it to the feed line at the other end. Signals arriving from the other direction are either absorbed by the terminating resistor or don't induce voltage waves in the antenna. What Hayes generally mean by multi-band antenna is a design that reconfigures itself electrically for each band of operation. The most basic one is the trap dipole. Each trap is a parallel LC circuit. At resonance, acts like an open circuit. Below resonance, like an inductor, and above resonance, like a capacitor. At lower frequency, the trap adds inductance to the antenna, making the antenna look electrically longer. At high frequency, the capacitance electrically shortens the antenna. Here's a example of what they look like. Essentially, traps are parallel LC circuits. They can be made from discrete inductors and capacitors, or may use coaxial cable or metal sleeves. The traps act like open circuits at their resonant frequency, causing different sections of the antenna to be active on different bands. This drawing shows a trap antenna that works on 10, 15, and 20 meters. The lowest frequency of operation, the antenna acts like a regular dipole shortened by the inductance of the trap. Yagis can also use traps to work on several bands. A 3-element tri-bander Yagi with traps and the elements works well at 20, 15, and 10 meters. Drawbacks. They do have drawbacks. Because it works on multiple bands, it radiates harmonics and spurious signals. And it's your responsibility to make sure those signals are not generated. They lose efficiency. And they don't radiate as well as a full-size antenna. You're constantly retuning them. They have a narrow bandwidth. So if you're let's say you're using on one on 40 meters, as you move one direction or another of the band, you might have to retune your antenna as you move. In other words, if you, let's say you're down in the CW portion of the band, and you've tuned your antenna, you move up. Let's say you decide to work FT8. You're going to have to retune because you're going to be your SWR is going to be ridiculous. It's however, saying that, my first antenna when I first started as a amateur radio operator was a trapped dipole, and it worked good. However, I didn't know any better at the time, and you know, and I, looking back, I'm trying to think of why I ever went with a trap dipole, because I did have room for a longer antenna, and I just can't remember why I had settled on a 4080 trap dipole. What is the characteristic of a random wire HF antenna connected directly to the transmitter? It must be longer than one wavelength. Station equipment may carry significant RF current. It produces only vertically polarized radiation. It is more effective on the lower HF bands than on the higher bands. Anybody?
I take a guess at A, alpha.
No. It's B. Station's equipment may carry significant RF current.
Okay.
In free space, how does the gain of a 3-element horizontally polarized Yagi antennas spaced vertically 1/2 wavelength apart typically compare to the gain of a single 3-element Yagi? Approximately 1.5 dB higher, approximately 3 dB higher, approximately 6 dB higher, or 9 dB higher.
I'll take a guess. B. Baker.
Yeah, Baker, 3
Oh,
dB.
boy.
What is the primary function of antenna traps? To enable multi-band operations, notch spurious frequencies, to provide balanced feed point impedance, to prevent out-of-band operation.
Alpha.
Yes, to enable multi-band operation. What is the advantage of vertically stacking of horizontally polarized Yagi antennas? It allows quick selection of vertical or horizontal polarization. It allows simultaneous vertical and horizontal polarization. It narrows the main lobe in azimuth. It narrows the main lobe in elevation. Yes.
D. Delta.
D.
I don't believe
Narrows
this.
the main lobe in elevation. Which of the following is the advantage of a long periodic antenna? Wide bandwidth, higher gain per element than a Yagi antenna, harmonic suppression, polarization diversity.
Hmm.
I'm gonna say A or B. Not sure.
A, wider bandwidth.
Hmm.
Which of the following describes a long periodic antenna? Element and length vary logarithmically along the boom. Impedance varies periodically as a function of frequency. Gain varies logarithmically as a function of frequency. SWR varies periodically as a function of boom length.
It's either A or C.
I'm gonna go with A.
Yeah, it's a element length and spacing are very logarithmically along the boom. What is the primary use of a beverage antenna? Directional receiving for low HF bands, directional transmitting for low HF bands, portable direction finding at high HF frequencies, portable direction finding at low HF frequencies.
Hmm. Uh,
What was that?
B.
Got to be
Baker.
A or B.
Ba- Baker. B. Baker.
It's a it's a low band antenna. Just remember that it's a low. It's usually considered a low band antenna.
It's receiving only too.
Yeah, receiving only.
Oh, that's the thing. Okay. So our beverage antenna is basically just for receiving then? Did I understand that right?
Yes, it's receiving only.
Okay.
Because it's right next to the ground. It's it's typically is 10 feet off the ground or so. So you know, which of the following is a disadvantage of multi-band antennas? They present low impedance on all desired design frequencies. They must be used with an antenna tuner. They must be fed with open wire line. They have poor harmonic rejection.
Bravo.
Yes, D, no, D.
D.
They have poor harmonic rejection. Okay, we're going to get into feed lines. We're getting close to the end. Balanced feed lines consist of two parallel conductors separated by insulating material in the form of strips or spacers. They have different impedances, characteristic impedances that characterize how electromagnetic energy is carried by the feed line. It's different from resistance. For our parallel conductor feed lines, the radius of the conductors and the distance between them determine Z. Z sub 0. The most common type is window line. The typical impedance for window line is 450 ohms. The most common characteristic impedance for coaxial feed line is our 50 ohm and 75 ohm. So here are some typical. Here's window line. Here's twin two lead. This TV. 300 ohm. hard line. So, with coax, you've got the center conductor, you've got a dielectric, an outer conductor, and a jacket of some material, the vinyl. Now let's talk about power and SWR. A feed line transfers all of its power to an antenna when the antenna and feed line impedances are matched. If impedances don't match, some of the power is reflected back to the antenna. Forward power, the power is traveling toward the antenna, and with reflected power, the power is reflected by the antenna. The power in the feed line is reflected at any point at which the impedance of the feed line changes. It can be either the antenna, a connector, or from a different type of feed line. The waves carrying forward power and reflected power form stationary patterns inside the feed line. These are called standing waves. The ratio of the peak voltage in the standing wave to the minimum voltage is called the standing wave ratio. Measures is how well the antenna and feed line impedances are matched. 1-to-1 is a perfect match, and none of the power is reflected. And the SWR equal to infinity indicates that all the power was reflected. SWR is always greater than 1-to-1. For example, 3-to-1 is, and not 1-to-3. SWR is equal to the ratio of the higher of antenna feed point impedance or feed line and characteristic impedance to the lower. For example, what is the SWR in a 50 ohm feed line connected to a 200 ohm load? And another example is what is the SWR in a 50 ohm feed line connected to a 10 ohm? What would this be? What is the SWR in a 50 ohm connected to 200 to it? What would that be? Anybody want to hazard a guess?
4-to-1.
It'd be 4-to-1. It can be measured anywhere along the feed line, but it's usually measured at the connection to the transmitter. It's measured by an SWR meter, which is often called a bridge. Transmitting equipment is designed to work at full power with an SWR at the input to the feed line of 2.1 or 2-to-1 or lower. Antennas that are much too short or too long will not work well, will have extreme feed point impedances causing high SWR. So how do you match the impedances? Matching feed line and loaded antenna impedances eliminates standing waves from reflected power and maximizes the power delivered to the load. But it's not always practical. The impedance matching is more often done at the transmitter end of the feed line. Devices used to reduce SWR are called impedance matchers, transmatches, antenna couplers, antenna tuners. Now, they don't really tune the antenna. It only changes the impedance of the antenna system at the end of the feed line to match that of the transmitter. In other words, an antenna tuner increases the power transfer from the transmitter to the feed line. In other words, it doesn't make your antenna any more efficient. If you've got a high SWR and you're able to match it, and so that your radio will work, doesn't necessarily mean that you've got a great antenna. There are devices constructed from inductors and capacitors that are adjustable by the operator. T-circuits can match wide ranges of impedances at the feed line connections to a 50 ohms that matches transmitter output impedance. It's important to remember that the SWR in the feed line between the impedance matching device and the antenna does not change. The device just changes the load going to the transmitter. SWR in the feed line stays the same. Installed at the transmitter end of the feed line, a T network, shown here, is designed to be used with unbalanced coaxial feed lines. This circuit uses 2 variable capacitors and 1 variable inductor. To use balanced feed lines such as window line, the output of a T network can be inductively coupled to the output so that neither of the feed line conductors is connected to ground.
You're gonna get it.
What's that? What, Carrie?
Oh, I'm sorry. I should be muted.
Heat lines dissipate a little of the energy they carry as heat, called attenuation or loss. Loss is measured in dBs per unit of length, usually a dB per 100 feet. Loss increases with frequency for all types of feed lines. The smaller the cable diameter, the higher the loss. Don't use 8X running from your house to your antenna out 100 feet away. Increasing SWR in a feed line also increases the total loss. The higher the feed line loss, the lower the measured SWR will be at the endpoint to the line. Now let's have some practice questions. What's the purpose of an antenna tuner? It reduces the SWR in the feed line to the antenna, reduces the power dissipation in the feed line to the antenna, increases power transfer from the transmitter to the feed line. All these choices are correct.
Delta.
All of them.
C,
Oh, see.
increases power transfer from the transmitter to the
Feed line. Increases power transfer from the transmitter to the feed line.
See, the trouble with this is this is wrong. See, the SWR in the feed line never changes. That's what makes D wrong. Z is wrong because A is wrong.
Transmitter to the feed line.
Which of the following factors determine the characteristic impedance of a parallel conductor feed line? The distance between the centers of the conductors and the radius of the conductors, the difference between the centers of the conductors and the length of the line, the radius of the conductors and the frequency of the signal, The frequency of the signal and the length of the line. Not hearing anything. Well, it's the distance between the centers of the conductors and the radius of the conductors. What is the relationship between high standing wave ratio and the transmission line loss? There is no relationship between transmission line loss and SWR. High SWR increases loss in a lossy transmission line. High SWR makes it difficult to measure transmission line loss. High SWR reduces the relative effect of transmission line loss.
Alpha.
I say Baker.
High SWR increases loss in a lossy transmission line.
B. Okay.
What is the nominal characteristic impedance of window line transmission line? 50, 75, 100, or 450? This is just,
Delta.
it's D, 450. That's just something you gotta just remember.
The higher one, 450.
What causes reflected power at an antenna's feed point? Operating an antenna at a resonant frequency, using more transmitter power than the antenna can handle, the difference between feed line impedance and antenna feed point impedance, feeding the antenna with unbalanced feed line.
C.
C, yes, a difference between feed line impedance and antenna feed point impedance. How does the attenuation coaxial cable change with increasing frequency? Attenuation is independent of frequency. Attenuation increases, attenuation decreases. Attenuation follows Marconi's law of attenuation.
Bravo.
Yes, it increases. And what units is RF feed line loss usually expressed? Ohms per 1,000 feet, decibels per 1,000 feet, ohms per 100 feet, decibels per 100 feet.
Delta.
Yes, delta.
Decibels per 100.
What must be done to prevent standing waves on a feed line connected to an antenna? The antenna feed point must be at DC ground potential. The feed line must be an odd number of electrical quarter wavelengths long. The feed line must be an even number of physical wavelengths long. The antenna feed point impedance must be matched to the characteristic impedance of the feed line.
Feed line connected to an antenna.
Should be delta.
Yes, delta. The antenna feed point impedance must be matched to the characteristic impedance of the feed line. If the SWR and antenna feed line is 5:1, and a matching network at the transmitter end of the feed line is adjusted to present a 1:1 SWR to the transmitter, what is the resulting SWR on the feed line? 1:1, 5:1, between 1:1 and 5:1, depending on the characteristic impedance of the line, between 1:1 and 5:1, depending on the reflected power of it at the transmitter.
Bravo.
Yes, bravo. It does not change. SWR in the
5-1.
never changes.
5-1.
What standing wave ratio results from connecting a 50 ohm feed line to a 200 ohm resistive load?
Alpha.
Yeah, alpha 4-1. What standing wave ratio results from connecting a 50 ohm feed line to a 10 ohm resistive load?
Delta.
Yeah, delta. 5-1. Well, that's the end of chapter 7, part 2 of 2. You are now experts at antennas.
Yeah.
Is there any questions?
I think it's fair to say antennas are a whole lot more complicated than this.
Yeah. I get
Okay, then. Well, I guess that about wraps it up. I will say two things about antennas. One is that when you start working with antennas with multiple elements like Yagi's, the math on that gets pretty crazy. And what you'll find is that a lot of people use modeling programs that do the heavy duty math. And even then, it's only approximations. The other thing about antennas is they work better if you put them up when the weather is terrible, or at
Yeah.
least that's what I've heard.
That's what mine did. Mine worked fine and on a stormy day.
Okay, so next week I will be talking about propagation. What happens to your radio signal after it leaves the antenna? So we'll have fun then. I hope everybody is trying the practice tests at least a few times a week at this point, because we are rapidly coming toward the end of the course. And 1 month from now, it'll be time to take the exam.
What chapter is that?
That is chapter that is chapter 8.
Next.
Oh, okay. All right. The ionosphere.
Yep.
Oh, okay, yeah. Propagation up at the top. Okay.
Okay. I promise at least a couple of really good pictures in the slides. Anyway, so that is the end of that, and I will say good evening to everybody.